Welcome. We will continue our discussion on the microstates of distinguishable non-interacting particles by considering now a system which is comprised of capital N simple harmonic oscillators, and each of these oscillators is present in one dimension, and we are trying to find out the number of microscopic states that are allowed for a system like this. So, once again we will start by looking at the case where there are only two simple harmonic oscillators present, and each of these simple harmonic oscillators we have already seen that they are characterized, their microscopic state is characterized by a single quantum number. Let me call that the particle 1 is characterized by a quantum number V1 and the particle 2 is characterized by a quantum number V2. Since these particles are not interacting with each other in a system where both of them are present, 1 and 2 are present, they will still behave as if they are on their own, but for the entire system you can still have V1 varying from 0 and taking up integer values up to infinity, and similarly V2 can also take up integer values starting from 0 and going from 1 to 3 and so forth. Now, the question that we ask is, for a composite system that is constituted by two such simple harmonic oscillators, then how do I define the microscopic state? The microscopic state obviously now will be defined in terms of two quantum numbers V1 and V2. So, let me have an example of how to define the microscopic state in terms of these quantum numbers. So, this is a typical microscopic state. So, all you have is a constant volume as shown by this blue box, and here I have highlighted the microstate of oscillator 1 and the microstate of the oscillator 2. Therefore, on the whole the microscopic state of this composite system of two oscillators, two one dimensional simple harmonic oscillators, will be given by V1 equal to 1 and V2 equal to 3. Now, the question that I ask here is, what is the number of microstates gamma if the total energy of the system, this particular system, is equal to something like n prime into h cross omega. Now, what is h cross omega? I have already mentioned that each of the simple harmonic oscillators, they are executing this simple harmonic motion with the same angular frequency omega. If that is so, in that case the energy values that are permitted for the particle 1 would be V1 plus half into h cross omega, and the permitted values of energy for the particle 2 are going to be V2 plus half h cross omega, correct. And now, in the composite system the total energy E is nothing but E1 plus E2, because they are not interacting with each other, and therefore, we can say that, well, if I have a system like this, then I must be having E is equal to E1 plus E2, and if the total energy is some number, some integer n prime multiplied by h cross omega, then n prime h cross omega must be equal to this relationship, and that is because I have written down explicitly what E1 and E2 are. So, this is V1 plus half h cross omega plus V2 plus half h cross omega, and this will give you V1 plus V2, then the two halves will make 1 into h cross omega. Okay. So, that is how we have arrived at the relationship that I have shown you here. Now, once I understand this, therefore, I should bother about the limiting condition here on the possible values of V1 and V2, and that has been highlighted over here. What I find here is for a given value of n prime, it must be equal to V1 plus V2 plus 1. Okay. Now, please try to understand, although V1 can itself vary from 0 to an infinite value, V2 can have an infinite number of options, but when they are together in the system and there is a restriction on the total energy, whatever values V1 and V2 can take up is now dictated by the fact that a relationship like this exists. This means that although I am supposed to vary V1 and V2 from their minimum value to their maximum value for all the infinitely possible numbers, here I should be able to vary only V1 independently, and V2, the value of V2 will always be decided by satisfying this equation. Now, let us actually take one example and see that what would be the number of microstates if I assign some specific value to n prime. So, let us assume that n prime is equal to 3, and correspondingly I will be having the total energy of the system comprised of the two simple one dimensional simple harmonic oscillators would be 3 h cross omega. And in this case, what I will be able to show is that then V1 plus V2 plus 1 is equal to n prime, that is equal to 3, or in other words, it is very simple to understand that here for all the microscopic states of the composite system having two simple harmonic oscillators, the V1 and V2 values would be such that they add up to 2. Now, this tells you that, well, what are the different microstates that are possible now? The different microscopic states that are possible, I can start with the minimum value of V1, that is 0. So, what would be the corresponding value of V2? That would be 2 minus V1. So, that is 2, and this is a typical representation of what the corresponding microscopic state would look like. As you see, the oscillator 1 is occupying the 0 point energy state, and the oscillator 2 is present corresponding to V2, sorry, this one should be here, V2 equal to 2. Similarly, we can think about visualizing the pictures of other microscopic states. So, this is a microscopic state where oscillator 1 is present with V1 equal to 1 and oscillator 2 is present with V2 equal to 1. And the third possibility is that the first oscillator is having V1 equal to 2, but the second oscillator is having V2 equal to 0. Now, V1 in itself could have been 3, but it cannot, it's not possible here because V1 plus V2 must be equal to 2 and both V1 and V2 are positive integers starting from 0. Therefore, the maximum value of V1 is associated with the minimum value of V2 and I have exhausted all my options. Therefore, in this case I can say that, well, the total number of microscopic states possible for E is equal to 3 h cross omega is equal to 3. Now, as you see that this expression or this kind of argument is very general. So, what we shall see next is what is the number of microscopic states that is possible when I have a general value n prime. So, this is the typical case for for capital N one dimensional simple harmonic oscillators, each having the same angular frequency omega. So, as you can see that, let me denote here this E prime as capital E by H cross omega. So, I understand that E prime is going to be some number like n prime. Okay. Now, if I have a microscopic state where the first particle, if I have a system where I have 3 one-dimensional simple harmonic oscillators. So, this is the lowest energy state that I can think of. All 3 oscillators are present with their respective quantum numbers equal to their respective minimum values, okay? And they add up to E prime, which is nothing but 0. Now, I am going to have here a pictorial representation of the situation that is going to be useful for us in the next part of the discussion. And here I have this as the typical representation of our microscopic state. I have a big box that I have subdivided into 3 compartments using 2 partitions. Okay. So, this is my partition number 1 and this is my partition number 2. And my idea is I am going to distribute 0 quantum of energy in each of these boxes. I mean, when I distribute 0 quantum of energy, I basically leave the boxes empty. And therefore, this would be a typical representation of the microscopic state where oscillator 1 has V1 equal to 0, oscillator 2 has V2 equal to 0 and oscillator 3 has V3 equal to 0. Now, let us consider the same system comprised of 3 one-dimensional simple harmonic oscillators, but now with energy that is equal to 1. Okay? E prime equal to 1 means that E is equal to H cross omega. Now, I can achieve this total energy in 3 possible ways. While the second and the third oscillators remain in their corresponding lowest energy states, I can have the first oscillator occupying the first excited state. So, this is V1 equal to 1. So, similarly, in this case, can I have a pictorial representation of the corresponding microstate? And that would look something like this. So, now you see we have the same box as before, that is separated into 3 compartments 1, 2 and 3 corresponding to the 3 oscillators, but now only oscillator 1 has 1 quantum of energy and this has been represented here by putting this red ball in the sub compartment 1. If this is so, then can I say that what would be the typical microscopic state corresponding to the pictorial representation corresponding to this microscopic state? This is going to look like this, and that is simply because the energy quantum now is 1 quantum of energy has been given to this particular oscillator, that is oscillator 2. Therefore, this red ball corresponding to 1 quantum of energy has been added to the compartment 2. Similarly, this is the pictorial representation of the microscopic state that is characterized by V1 equal to 0, V2 equal to 0 and V3 equal to 1. Now that we have introduced this pictorial representation, let us move over and try to see what is going to be the pictorial representations for the case where the E prime value is equal to 2. Please try to understand that here I am taking the 0 point energy as the 0 of energy scale, and therefore, E prime is going to be just an integer. Now, coming back, what I find here is something very interesting. What I find here is here 1, 2, 3, 4, 5, 6. There are 6 different ways in which the total energy of the system will be equal to 2. Now, what is a typical pictorial representation of any of these 3 states? Here as you see that if I just take this state, here you will find that the first oscillator has 2 quanta of energy, the other 2 oscillators do not have any quantum of energy assigned to them. And correspondingly, the pictorial representation of a typical system like this would be given by this picture. As you see that oscillator 1 has 2 quanta of energy associated with it, and therefore, you can see that there are 2 red balls presenting the 2 quanta of energy in the compartment 1 allocated to the oscillator 1. These 2 do not have any energy, I mean any additional energy other than the 0 point energy, and therefore, each red ball which represents the quantum of energy over and above the 0 point energy, I do not have anything here. Similarly, you can see that these 3 energy states are also similar. They are similar in this way that here you have 2 particles having 1 quantum of energy each, but the third particle does not have any. So, under such condition, what you find is the pictorial representation of a typical microscopic state would look like this. So, here the particle 1 has 1 quantum of energy, the particle 2 has another quantum of energy, and the particle 3 has none above, over and above its 0 point energy. So, then the question is, as we can see as before, that the number of microscopic states, they depend on the total amount of energy that is available to the system. So, here I find that, well, we have already seen when n is equal to 0, gamma is equal to 1. When n is equal to 1, gamma is equal to 3, and when n is equal to 2, gamma is equal to 6. And what is it going to be when small n is equal to 3, which means if small n quanta of energy has to be distributed amongst all the microscopic states, how many microscopic states are possible? The answer is 10. So, the question is, well, you can go on drawing the different microscopic states like this. For example, one of the microscopic states, when I am going to distribute 3 quanta of energy amongst 3 oscillators, these are going to be like this. I can have the system, I have 2 such separations giving me 1, 2, 3 subcompartments for the 3 particles. So, one possible microscopic state is this. All the 3 quanta are present for particle 1, no energy energy quantum available for particle 2 or 3. I can also have the situation where particle 1 has 2 quanta of energy and maybe particle 3 has 1 quantum, particle 2 does not have it, or it may so happen that each of the particles will have 1 quantum of energy each. As you see, in each of these cases, first of all, you can build microscopic states like this in at least 3 different ways. What are the different ways that you can do it? The other 2 states are going to be like this. So, the particle 2 is going to have both the all the 3 quantum of energy, and the particle 1 and 3 will not have anything, or else you will have the particle 3 having all the 3 quanta of energy, right. The next, so I have 1, 2, 3 such states where all the quanta of energy available has been taken up by one simple harmonic oscillator. Now, about this, you can have other microscopic states like this one, or you can have something like this, or you can have something like this. Is there any other possibility? Yes, I think I am leaving out one more possibility, and that is I will leave this to you to figure out what are the other possibilities. So, that is a homework. But the point that I would like to highlight over here is this: each microstate in my representation has small n quanta of energy, where each quantum of energy is represented by a red pellet like this. And these are going to be distributed over capital N particles, and these n particles are separated by capital N minus 1 walls, and each of these walls are represented by a black vertical line like this. In this case, if the numbers for a general case capital N and small n, what is gamma n? Gamma n is the number of ways in which small n symbols may be chosen as the pellets out of a total number of capital N plus small n minus 1 symbols available. Okay. So, basically while constructing this kind of a picture, what you were playing around with is 3 such balls and 2 such balls. Okay. So, what is the total number of particles? The capital N is equal to 3. How many quanta of energy do you have? That gives you small n, and small n is equal to 3 here, chosen arbitrarily. Now, the number of such separators, how many are there? That they are given by capital N minus 1, which is equal to 2. So, what are the total number of symbols that you have? I have represented them here. I have 1, 2, 3, 4, 5. I have a total of 5 symbols, out of which I will have to choose 3 as pellets. Okay? And that can be done in a way that I will say that this would be 5C3. Okay? And this can be evaluated as factorial 5 by factorial 3 into factorial 2. So, that is 5 into 4 into 3 into 2 divided by 3 into 2 into 2. So, the result is 10, and I leave it to you to figure out the different microscopic states that are possible when you have capital N is equal to 3, small n is equal to 3, and the total number of microscopic states is equal to 10. I have already drawn quite a few. So, basically what I am doing is I have taken these 3 balls and then taken these 2 separators and placing them either on one side or like this or like this. So, basically I am playing around with the total 5 symbols that are present with, that are available to me, and either fixing the position of the 2 balls and distributing the 3 red balls separately, and that is exactly how these number of microstates are counted. But you must also realize that in the case of the spins, in that case if I wanted to find out the kind of pictorial representation, I have not done that. But here this kind of count, because there the counting was very easy, but here I am doing it simply because, as you see, that here there is no restriction as to how many balls or how many quantum of energy that you can put in a given box. Here I have put all the 3, here I have put only 1, and in this case I have put two of them in one box. So, this kind of counting becomes useful when you have no restriction as to how many quanta of energy can be accommodated by each particle, or that means that each of the particles can have an infinite number of options as far as their own microscopic states are concerned. So, in this case we have learnt several new things, and what we have learnt over here is if capital N is a large number, then gamma is going to be a very large number indeed. So, small n, that can be a large number or a small number, but the microscopic states, number of microscopic states for a given system with a given quantum of energy is still going to be very large. And in that case, once again you can use the Stirling approximation to find out the natural logarithm of gamma. So, in conclusion, what I would say is as follows. We have learnt now that if the macrostate of a system is defined by giving some specific constant values to its thermodynamic variables like the total energy V and the number of particles, and if n is a very large number, typically of the order of 10 to the power of 23, in that case for every macroscopic state there is a very large number of microscopic states possible for the given thermodynamic state of the system. So, that is a very important observation and provides us with the fundamental concept in developing the language of statistical mechanics. In the next class, we will see how statistical mechanics can be used to connect the microscopic states to the thermodynamic properties of a given bulk system. Thank you.